Hey everybody, so this is a unique research paper that caught my eye. Neural manifolds and cognitive consistency, a new approach to memory consolidation in artificial systems. Up front, uh, I am an engineer and doctor, and then so dang it, Jim, I don't fully comprehend and understand the psychology behind all of this. I had to look up a lot of it. It's based off of Heider's theory, Heiders, and I'll get into that. I'll dive into it, but what they do is they give all of the mathematical equations and then they give me beautiful charts, and then so this is like what I should be optimizing towards, and then all of the equations, and then this is the initial state, and then this is again what I should be optimizing towards. So I know how to read this, right? I don't know I don't know psychology and the biology behind it. But they say that it's for like memory consolidation, and like it's based off of this Heider's theory, and then so Heider's theory is like balance theory, and then Heider reasoned that object configurations, including social objects, could be classified into those that are in a balanced or an imbalanced state, and that balanced states are preferred to imbalanced states because they form good figures or simple structures. And then so balanced states versus imbalanced states would be like if person A likes something and person B likes something like a movie, then that's a balanced state. But if person A likes the movie and person B doesn't like the movie, that would be an imbalanced state. And then so the creators of this paper, they translate all of that into mathematical equations, right? And then so they take this balance theory and then they build a full framework off of it, and then they build a full mathematical framework, and it's very cool, very intricate. Thank you guys. And then so what I do from there, right, is just like kind of what I do now, kind of like second nature, is turn mathematical frameworks like that into code and into something practical. So here's the practical implementation of the mathematics that they provide within that. And then so I gave it out like it's divided out into the mathematical equations, right? So like I'm just literally taking their math. So the neural manifold representation, the simulating SPWR events and memory replay. And then so again, like I don't know the psychology behind it, but they gave me the math, right? So just give me the math, I'll do it. And then 3 is a balance energy function for cognitive consistency. 4 is synaptic weight optimization with balance constraints. 5 is memory consolidation via Hebbian learning. Again, like I have heard of Hebbian learning, and it's like I know that concept and I know to pronounce it correctly, but that's as far as I can go with that. But they give me the math, right? So I'm just here's the math for Hebbian learning, and then so I just apply that, and then I go through, and then I execute it, and I put it all together, and cool, it looks pretty, right? That's kind of the goal front. And then so let me actually put it into like something practical, right? Into like so like they explicitly lay out how to do this mathematically, right? So I'm just taking again all of their math, so translating this into a brain, right? I create a brain like with 1,000 neurons, and then I'm going to train it for 10 trial blocks. I have the time steps for so SPWR. At this point, I know that it's very important within the cognitive framework of this, and then so and it relates to time and how like it's kind of like a wave function, which is why I like it, and how that interacts within the brain is my engineering understanding of it. And then the rest is just like balancing weights and forming stability within this brain structure, right? And then so I take these concepts, and then they also introduce this equation, this wake-sleep interaction. And then so if you like a few weeks ago, I put out a concept, artificial sleep, and then like I think there's a something to that when you like I'm just as an engineer, I understand that biological organisms sleep, and then if I'm trying to put biological stuff into a brain, it seems to me that that's something that I would want to put in here. And then these guys, again, who seem to know a lot more about this than I do, beyond just the mathematics, seem to agree with that, and they build that in here too. So I think that's pretty cool. And then so I'm just highlighting that. And then so you can see how this system, so this is my first test with the system, and so this is a very bad test. If you cannot read this, this is working the exact opposite that the authors intended it to be. And then so what happens is that within how this functions from an engineering perspective is very simplistically when you get the output, right? You get an energy reading, and then I want the energy to actually go down within the system because energy going down within the system, it means that the system is self-organizing. Energy going up in the system, it means that there's chaos being introduced. So the system is like in a relatively stable state in this initial state, and then I train it, and then it's like, what is this training? What are you doing to me? And then it never figures out what's going on. It's kind of what happens in this first test, and then we get a reflection of that, and then we get this weird synaptic weight distribution, which is like this, right? And this is like their bad test. And then so I'm like, okay, I see there's some stuff wrong here, and it's not mapping very well to this knowledge. So let's make it better, right? And then so I just go through and I just iterate, right? Iterate on like kind of the structure of the code. Again, they give me all of the math. So the beauty is I don't have to iterate on the math in this instance. Like I know the math is right? It's something that I'm doing within the code. And second test is a lot cleaner, but it's like a different problem, right? So second test is like I get initial energy, and then like a slight spike in the initial energy, and then like the slightest reductions on the planet, right? Like this would essentially measure like zeros, almost near zeros across the board. But it's something, right? And we can see here we're starting to get this more to this what we want it to be, which again like is this, right? Or this one here, the synaptic weight distribution evolution, or same thing, synaptic weight distribution evolution, and that one looks a lot like ours, right? So we go here. We don't have like the rise in the middle. We have a crater in the middle instead, but it looks pretty similar, right? But what we really want is those like towers on the side. And then so, okay, cool. So I'm getting closer. Let me optimize it one more time. And then so go through, and then again, just, I add gradient clipping. So I should highlight that. So like the one part of the math that I add within this is I do gradient clip, right? And then that's just like, to like, I notice that gradients are exploding in these equations, and then so I just gradient clip just to deal with the exploding gradients. And then doing that and a few other tweaks, I get the model to perform how they want it to, right? So here, this looks good. This looks like more like what they had there. This is looking closer to what they had. And then same thing with the synaptic weight distribution. It's not evenly distributed for some reason. So there's still some optimization I think that could go on here, but this is what the math is supposed to do, right? So we see a high initial energy score, and then as it goes through each iteration, energy is going down, and then it's balancing itself, right? So the system is self-balancing according to these memory operations, and then so according to this self-balancing function and the framework that they set out, this Hyder reasoning framework, it is self-balancing all within this system. And so this notebook is representative of their mathematical equations within it. Again, this is all tied to memory, right? So this is giving the model's memory according to this Hyder model, which again, I don't fully understand the full biological and psychological implications of that, but I saw a bunch of math and pretty graphs, and I decided to reverse engineer it. And then so it looks really cool. I like the framework overall. So here it is. And then here's the framework for anyone. I'll leave a link to both the Colab notebook and the paper, so you have both the math and the code. If this excites you in any way, here you go. I don't know what to do with it further, honestly. I hope that someone does. I'm sure that there is. And then if you like this type of content, please like and subscribe. Thank you very much.